Shall we start? Yes, please. Okay. Here is another presentation. It's from Professor Theofilos Papadopoulos in the me. Theofilos Papadopoulos is an associate professor in the Power Systems Laboratory in the Department of Electrical and Computer Engineering in Democratic University of Thrace. And I'm a principal engineer in the R&D department of HELLENIC cables. This presentation deals with some modeling aspects that need to be considered in sheath bonding, mainly in underground power cables, and how have we investigated these aspects using the EMTP software. Let's start with an introduction. As we all know, we have recent advancement of renewable energy sources, both in onshore and offshore grids. Thus, there is an interest in the application of power cables in several, let's say, topics regarding the electromagnetic interference in general under the umbrella of electromagnetic interference. We are interested in current rating calculations, of course, in order to dimension these power cables. And one more thing is the overvoltage that might arise on cable sheaths, also in bonding leads and in joints that connect different cables between. As we saw in the previous presentation, there are several bonding designs and schemes that can be adapted and are proposed in the literature. There are several papers, different SIGRE brochures that analyze this aspect. There are three main categories, let's say. The first one is the single point bonding, SPB, we have named it SPB here, where one of the end of the cable and the metallic sheath is open circuited. The other one is the solid bonding, where both ends are bonded and grounded. And the third one is the cross bonding scheme, where we have, in the ideal scenario, 1/3 of the cable length and as a minor section, and we have three minor sections where the sheaths are mutually interchanged. The cross-bonding scheme especially has different slight variations. It can be, let's say, the sectionalized, the direct one, and several others. I think you can find them in the SIGRE Technical Brochure 797, which have been published later. Now, in order to calculate the induced sheath voltages, depending on the bonding scheme, there are several guidelines and formula in the literature. For example, there is the well-known IEEE standard 575, and some others in SIGRE publications. And of course, we can also perform some simulations with the EMTP software in order to calculate and estimate both the induced sheath voltage and the induced sheath current. Of course, if we use, let's say, some formulae, analytical solution, and all this stuff versus the simulation, we have a trade-off between accuracy and complexity as a model. The scope of this presentation is first to systematically investigate the different modeling aspects regarding the calculation of the sheath currents and the voltages in the EMTP, and secondly, to highlight the parameters that can be neglected or are necessary in the modeling process of the steady-state solution. So there will be a parametric analysis with various parameters, with various variables in order to see their impact on the voltage and the current. As a case study, as a cable system, we selected an underground cable system of 3 medium voltage single core cables. You can see here their arrangement. It's in a trefoil arrangement. You can see also the type, their name. They actually consist of aluminum. They also include XLPE. They have as a screen sheath, metallic sheath, an aluminum foil. And also there is also an HDP jacket. Their nominal voltage is 1830 kilovolts. And here you can see the modeling of this specific case study in the latest version of the EMTP. Of course, we use the MOMS modeling in order to have the flexibility of turning on and off the proximity effect. And we have also the ability to include or exclude the earth intern path. These cables are mainly used, at least in Greece, but I suspect in the other countries too, to interconnect the onshore wind parks to the main grid. And here you can see a sketch of this connection. On the right, you can see the wind parks that form a 33 kilovolt bus bar, and we will have up to 4 such cable systems that are connected, let's say, in parallel. And then we end up to the substation 33 kilovolt bus bar, then to the transformer, and to the main grid. Now we have to discuss a bit about the mechanism that can be triggered in such cables in terms of modeling. First, we can, let's say, trigger the series impedance of the corresponding PI equivalent of the cable. Thus, this trigger is called an inductive trigger, the inductive mechanism, where the nominal current is actually injected. And this inductive mechanism is actually described in the majority of the standards technical brochures, either in SIGRE or in the IEEE, and also in the IC standard, which deals with the current rating in underground cables. Then, of course, we have the capacitive effect, the charging effect, where we actually trigger the shunt branch of the PI section, and we trigger it with the nominal voltages. And then we have, let's say, the full coupling, where we trigger both the series impedance and shunted admittance tracks matrices with a nominal voltage and a nominal current. So, as a first case, we assume the single point bonding. You can see here on the left, on the figure A and figure C, the voltage, the induced voltage, and on figures B and D, the induced Sheath current, where we have 2 different cable lengths of 500 meters and 5,000 meters. And the first, and we actually inject all 3 mechanisms, namely the inductive, the capacitive, and the full coupling one. So the first observation is that the Sheath voltage, as we can see in figure A and C, is mainly influenced by the inductive coupling. We can see this because, let's say, the blue cube follows the red one, which is the inductive one. And the effect of the capacitive coupling, which is indicated with the yellow one, is actually pronounced only in the second case, where we have 5 kilometers of cable length. Thus, we can say that the capacitive coupling increases with the cable length. This is expected since as the cable length increases, we have the accumulation of the charging current, and thus the capacitive coupling is more pronounced. On the other hand, the Sheath current is mainly influenced by capacitive coupling. This is also evident because since we have a single point bonding, the inductive coupling actually gives no current, since one of the ends is open circuited. So the total current comes only through the charging one. Now, if we compare this modeling, the full coupling of modeling, versus the inductive coupling, which is calculated using the IEEE standard, we can see that in terms in the results, in terms of relative error, we have a very small relative error in the first case of 500 meters, and a large one in the case of 5 kilometers. This is also expected because, as we said before, the capacitive coupling is pronounced when the cable length increases, and this is the case where the IEEE standard actually fails, since it considers only the inductive mechanism. So an engineer, a cable specialist, must be aware of this fact and be careful when he is using the IEEE standard or any other standard that actually implies that it only takes into account the inductive effect, especially if he is going to apply it to some cables that have bigger lengths. Then we move on to the solid bonding case. Here, the trend is, let's say, it's actually a dual trend. So again, we can see that here we can see that the sheath voltage is mainly influenced by the capacitive coupling. You can see on Fig A and on Fig C that the blue curve actually follows the yellow one, which is the capacitive charging effect. And the sheath current is mainly influenced by the inductive coupling. We have a strong induced current. We have a way smaller charging current. So the geometric addition of these two currents, in the geometric addition of these two currents, actually the inductive current prevails. Again, if we try to compare the full coupling which has been simulated in the EMTP with the inductive coupling, which is simulated both in EMTP and with the IEEE standard, again, we can see that at small length, at 500 meters, the error is small. And if we go to the 5 kilometers, the error again goes high due to the inclusion of the capacitive effect only in the full coupling of the version of the model. Finally, we go to the cross bonding. Here you can see we have simulated a fixed length of 18 kilometers, and we actually change the number of major sections. In Fig A and B, you can see the sheath voltage and the sheath currents for one major section, while in Figs C and D, you can see the corresponding results for 4 major sections. We can see that the sheath voltage is again influenced by the inductive coupling. The blue curve follows the red one. And we can also see that by increasing the number of major sections, the effect of the inductive coupling and the capacitive one both reduces, and the induced current is also reduced, thus the capacitive current becomes, let's say, more important. Here you can see that the error stays at the same level when changing the major section from 1 to 4, and this is justified, but from what we said before, that the main mechanism here is the inductive one. So,
okay. So we started doing also some parametric analysis in order to investigate the effect of different factors. The first one is the proximity effect. Within this is possible by using the Monzo model. So the results here are presented for the solid bonding and the cross bonding cases. For the first case, we assume a 5 kilometer length, and the second one, the 18 kilometer length as previously. And we apply the full coupling here, and we plot with the red color the results obtained by neglecting the proximity effect, and with the blue color the results with the proximity effect for both formations, for both bonding designs. And we can see that we have some differences in the current for the solid bonding and for the voltages, which are generally at the level of 3%. Of course, because this is a trefolding case, the differences are observable. Let's say they're not that high, but they might be of interest from a technical perspective. So, but if we move to a flat arrangement or to a space trefold formation, Of course, you can understand the effect of the proximity effect would be negligible and can be neglected. Okay. So next we have examined the effect of the number of parallel cable circuits to show that the inter-array cables that connect the waiting part and the main grid are multiple. In most analysis, especially when a company asks from a designer or a researcher to investigate the use voltages and currents, typically they can say that okay, they are isolated, so more or less we can neglect their influence. Of course, this is also neglected in the technical brochures and the IEEE standard. So here we have examined the case that we have. We examined the voltages at one specific circuit by adding 2, 3, and 4 parallel circuits. And the spacing between the cable systems is 0.5 meters. Again, we assume full coupling, and also there are two kinds of arrangements when we have parallel circuits, the unsymmetrical and symmetrical. It depends. This has to do with the phase sequence between the cable phases. So we have examined both cases, and for the voltage and the currents for the single point design are not significantly influenced, so they will not be presented. But for the solid body, you can see here, these are the currents, the profile of the voltage along the cable sheaths, the corresponding currents, and for the unsymmetrical and symmetrical cases. And you can see that, okay, there are some differences in the voltages for both the unsymmetrical and symmetrical cases. For the solid point design, the major problem is, of course, it's not the voltages, because you see that the levels are very high due to the bonding scheme at both ends. But you can see that there are indeed some differences which are significant by taking into account the additional circuits. You see, for the original case, with one circuit, the current is the level is here, and by adding circuits in the asymmetrical case, you can see that we have a reduction, which, okay, it might not be it might of interest for the current rating case, but also when we are doing the analysis in order to end up to the proper bonding scheme, because you see that the differences are in the level of several amperes. And accordingly, we can see we have recorded differences also for the symmetrical case. Now, moving to the cross-bending bonding case, we see that for the unsymmetrical cases, practically the voltages are identical, although we have some differences here for the symmetrical case, but also we record significant differences regarding the currents, which is a major issue. Remember that cross-bonding actually is applied in order to reduce the cable losses and not for safety reasons. So this is, if we want to be precise, we have to take into account also the additional circuits that running in parallel with the outtake design. Next, what we wanted to investigate the earth continuity conductor ECC. It is a conductor that it is used mostly, definitely with the single point bonding case and the cross bonding case. With the solid bonding case, this actually it's an additional conductor which helps to reduce the resistance. And it is used for the cross bonding and the single bonding case in order to put the SVNs. So we have compared 3 cases. The first case that we neglect the ECC from our analysis. In the second case, the ECC it is installed very close to the cable system, so it touches the cable system. And the third case, the ECC is below the cable system. There is no a specific guideline in either SIGRE or IEEE whether exactly we should put the ECC. So we investigate this influence at different case locations. In the first graph, you can see that actually we have symmetrical voltages induced at the cable sheaths. But when we introduce the cable, the ECC, and especially when it is when it is starting the cable system, you can see that we record differences between the phases. This is logical. This is clear because the ECC, the additional current that flows through the ECC, deteriorates the symmetrical, the balanced case voltages that we have in the original case, and we can record differences, different profiles between the three phases. Of course, the influence of the ECC reduces as its location is away from the cable system. So the ECC also in the analysis of induced voltages and for the current range should be taken into account, because we may go beyond the limits that the national or the international standards allow for or propose for the induced voltages. So these are parameters that typically are neglected from the investigations. Another thing is the neutral earth resistor, which is actually most people think that it is the earth substation, but these are two different ones. The neutral earth resistor is connects the neutral point with the grounding of the system, and it is used to reduce the single pole faults. For the 33 kilovolts and for the Greek system, its value is 19 ohm. In order to reduce the single pole to ground short circuit to 1 kiloampere. This is practice that our operators follow, and this is the resistance of the substation. So the influence, it has a negligible influence to the shift voltage and current, because for the steady-state case, for the normal operating case, and this is because here actually when we have a normal operating case, we don't have a flow of currents to earth. But this parameter is very important when we have to investigate an asymmetrical case, either in the normal operating condition and definitely other faults. So, but for the solid body case, you can see that we plot here the results without ECC and with ECC. Here are the voltages and here are the currents. What is interesting to note here is, okay, the voltages again are very low, the voltage levels, but you can see that we have a completely different profile when we use the ECC and with neglected compared to the previous case. But in any case, we see that we have the influence of the neutral electric resistance is negligible, especially in the voltage. We have some very small differences here in the currents because of the slightly asymmetry in our geometry. Also, we have investigated the grounding resistance. This is for the substation at the ends. So we have assumed 4 circuits routing in parallel in the asymmetrical phase sequence. The ECC is neglected here, and we have a full electromagnetic coupling and varying the grounding resistance. The result for the single point bonding case and the cross bonding designs are practically unaffected by the grounding resistance. This is as expected because of the symmetry in our arrangement. But for the solid bonding case, we can see that we have some small differences in the recorded voltages you see here. But for the currents, the differences are negligible. So these were our preliminary results about the normal operating conditions. But we move a step forward. We are doing now some investigations regarding the short circuit cases. So here we assume only the inductive coupling because it's the predominant one. And we have applied a 3-phase short circuit of 6.6 kiloamps. This value has been selected because this is the maximum withstand the maximum current that can flow through the sheaths. And for the single pole to earth case, the full current is 1000 amperes. The 760 amperes, it's the normal operating current. I've put this value here in order to realize that we do not have a significantly as unbalanced case as we would have expected for the single pole case. And here we plot first the results for the solid body case. Additionally to the trefoil arrangement, we have assumed the flat arrangement, so we have exactly the same single core cables, but they are not put in trefoil formation, but in flat formation with the cable spacing of 0.5 meters. And we plot here the voltage, the sheath voltage profiles for the trefoil and the flat formation, and the current profiles here and here. Let's start from the currents. We can see that the orange curve is the steady state case. The blue curve is the single phase short circuit case, and the three-phase short circuit case is the yellow one. Here, the currents, as Andreas previously said, they are mostly influenced by the inductive coupling. So we can see that moving from the steady state to the single pole to the three-phase case, we have an increase at the voltage level. And for the voltage profiles, you can see that we have a difference depending on the profile pattern regarding in terms of the asymmetry in the circuit. What I mean, you can see here, this is the steady state voltage, okay? You can see this kind of voltage, this kind of profile. In the three-phase short circuit case, again, we have a symmetrical case. We have almost the same, but with lower level. This is because we neglect the influence of the capacitive currents here. But when we have the asymmetrical case, we can see this V shape that also Pauline and Fred mentioned two presentations before. So you see how this changes, or how the asymmetry changes the values, but also the expected profile. Okay. So, but in the flat arrangement, what I'm saying is also verified because we have an asymmetry in geometrical, an asymmetry now in the out geometry. You can see that we get again this V shape. Again, because here we have the inductive coupling, it's the same remarks as for the trefoil case also can be used. Now for the single point case, again, we see that the voltages, because they are mostly influenced by the inductive coupling, we have the lowest voltages at the steady state, of course. Next comes the single point, the single pole ground case, and finally the three-phase case. Of course, we get higher voltages because of the level of the current is. We have here 1000 amperes, and here for the three-phase case we have 6.6 kiloamps. But in cases where we would have a high asymmetry in the single pole case, these results might be vice versa. Again, here we have recorded here the differences in the currents. Remember that in the single point case, single point bonding case, the cable sheath end is open-ended, so here we got a zero value and we have the maximum value at the point where we have the grounding. And moving on to the cross-bonding case, again, we see that when we have the inductive coupling being the predominant one, the highest voltages, this is for the voltage, these are reported for the three-pole to ground short circuit case. And again, we see that we have similar for the trefoil arrangement. We have similar current levels for the steady state and three-phase short circuit, but because of the asymmetry here, this is very important. For the cross bonding case, we get a very high current level value. More or less, the same remarks are deduced for the flat arrangement. And of course, a general remark, you see that for the induced voltages for the case of the flat arrangement are significantly higher compared to the trefoil because of the geometrical asymmetry. So these were, as we said, the preliminary results. We are working on this area these days. We are also performing comparisons with syntax, and we are hopeful that we are going to publish our remarks and our results in the next months. And we have a systematic comparison between different software like EMTP and the different assumptions, as well as syntax. And what we have seen from these results is that for the normal operation, we have done a systematic investigation of different modeling aspects. For the single point bonding and the cross bonding cases, we saw that the sheath voltage is mostly influenced by the inductive coupling, while the sheath current by capacitive coupling. The opposite behavior is observed for the solid bonding case. As the cable length increases, the capacitive coupling becomes important. So, that's why we have recording this difference with the IEEE standard. So the technicians must take that into account in their analysis, because they will make this if we neglect the capacitive current, we may end up to significant errors. The cable systems that route in parallel may cause significant EMI to nearby cable shifts. This was more pronounced when the single bonding and the cross bonding designs are considered. In such cases, the applicability of the IEEE standard is limited. And these parallel routing can significantly influence the induced sheath voltages and currents, especially in the solid bonding and the cross bonding cases. The ground resistance does not play a significant role in this analysis, but definitely in short circuits. And in short circuits, we get higher voltage and current levels in the flat formation due to the geometrical symmetry. And for the single three-phase short circuit case, the results we got are higher for the cross bonding and the single point bonding designs. And for the solid bond design, the highest induced sheath voltage level differs regarding the cable formation. And I have added one extra slide, but I forgot. All these calculations, especially the per unit length parameters, we have implemented me, Andreas, and Amauri toolbox in MATLAB, where when one can do different kind of can calculate the parameters, lines, cables, and perform some steady state and transient analysis. Some results have been presented also in our first presentation, and what is most of interest for the EMTP users, we have also added a functionality that exports data that can be directly incorporated in EMTP, and especially in the wideband model, and can perform also simulations with the EMTP. So there's coupled this our toolbox coupled with EMTP, thanks to version 4.0. So this was our presentation. Thank you very much.